In this video, I am going to show you the complete detailing and design of columns, which is a part of special moment resisting frame. The given framing conditions are shown. C1 are exterior column and C2 are interior columns. The FC prime and FY is 4 and 60 respectively. Floor heights are 10 feet. It's a two-story structure. The center to center span is 18 feet and the slab and beam dimensions are shown. Live load 40 psf, SDL load is 20 psf, the seismic zone is 3, soil type is SD, moment resisting frame has to be designed, and the building is residential building. We have to use UPC 97 for seismic loading. We have to calculate the column sizes, its reinforcement, and the detailed drawing, and use ACI 31814 for design. Let's start with the rough dimension calculation. The smallest cross-sectional dimension for a special moment resisting frame is 12 inches and the ratio of shortest to largest dimension of column is 0.4. The maximum column catchment is 18 by 18 feet and the ultimate load is calculated as 208 psf using this catchment area. The maximum point load is 208 into 18 into 18 gives us 67 kips. The cross-sectional area of the column is typically calculated dividing by a fraction of FC prime. So the column dimensions comes out by 7 inch by 7 inch, but definitely we will take dimensions minimum as 12 inch by 12 inch. So the beams are already defined as 12 by 12, so the columns shall be typically larger in size than the beam for SMRF. Defining the grids right now for the given situation. The drawing is on CAD for detailing. We will be starting to define the properties with the materials. The rebar properties, let's name it as G60 deformed bars. The concrete strength is 4 ksi or 4000 psi. Checking the modulus of elasticity of concrete. So the modulus of elasticity is same. Now we will be defining the sections. Let's first delete the useless sections which we will not be using in the design. These are steel cross section defined by ETABS by default. Starting with the rough sizes we calculated. Let's say the minimum size we selected is 14 inches. Adding the property modifiers using ACI code to incorporate the crack moment of inertia. Reinforcement to be designed is selected as we desire that ETABS itself design the reinforcement. Delete this section. Now the next larger size we select is 18 by 18 inch. Reinforcement to be designed is selected. This part becomes useless if we have selected reinforcement to be designed. If we selected reinforcement to be checked, then the part would have been effective. C21 by 21. Let's add new property of auto select list, or first we add the property of the beams. The property modifiers of the beam according to ACI code. Since we don't want torsion in the beam, on very less torsion, so we are taking modifier as 0.001. Design is to be as beam. Okay. Now we will be adding an auto select list so that ETABS select the appropriate cross-sectional size of the column which is most adequate. You may also choose to select the size from which the ETABS will start the iteration. Right now I have selected medium section by area, so ETABS will start with the smallest cross section first. There was one thing which we could have done, that define the interior and exterior columns individually so that we may use the tables for design, which would have been a lot easier. Let's define interior and exterior columns individually so that we can use a shorter way to design the columns. Let's name it as interior. And the leftovers will be exterior. For instance, we will name this as exterior. In the later part of the video, you will understand why I have done this, and it has made the problem a lot easier. It's exterior because the list includes exterior columns. Now it is interior, so we have to modify the list and add the interior ones by pressing and holding the control button. Now we have to find the columns cross sections. Now we will be modeling the structure. Auto select exterior for exterior columns. Exterior columns are present here as well. So the rest are interior columns. Defining the slab section as given in the situation. In order to understand the difference between shell thin and membrane, you have to go to the video whose link is given in description. Applying the property modifiers using ACI code. Now the next thing is we will need to draw the beams in the plan and then the slab so that the model will be complete. Let's first start with defining the load patterns. Let's call that load as SDL, which we were given with. Earthquake in X direction. Earthquake in Y direction. Earthquake X direction for drift check. Earthquake in Y direction for drift check. Modifying the lateral loads using UBC 97 parameters. Soil type was SD and the seismic zone is using UBC 97. Since the zone is 3 and the moment resisting frame is type is special moment resisting frame. Seismic zone factor 0.3, coefficient of acceleration 0.36, coefficient of velocity 0.54, the value of C2 for concrete is 0.03, and the value of strength reduction factor 8.5, and importance factor is 1 for residential structure. (8.5) is already input here. The same load pattern will be defined in EX and EY drift case, but the only difference will be the case multiplier, which we will be modifying in the next step. So we are done with specifying the earthquake loads. Now we have to go to load cases. Go to EQX drift. You have to check the limits for drift due to seismic loading, drift due to wind loading, and torsional irregularity for design of lateral force resisting system. Since it's low rise, so drift due to wind is not defined and torsional irregularity will not govern. But we have to know how these checks are applied, so for that you need to go to the channel and watch those videos. For seismic drift check, we have defined the case already. The seismic drift ratio has a limit implied by UBC 97. For that, we need to know how to define the case. The maximum inelastic drift is computed as follows: 0.7 into R into delta S. That becomes 5.95 for the case multiplier. So we have to incorporate in our case. But since we don't want this case to be incorporated in the design as it is just a serviceability check, so we have to go to the design option and click on the load pad type as other, so that it's not considered in design. Now you have to define the mass source. Using the dead loads. We would have taken live load in case of high-rise structure, the 25% contribution from the live load, but it's not a high-rise, so we will leave it as it is. Now model the beams in the structure. and also the slabs. Now I need to mesh the slab. The maximum mesh size shall be 3 feet. So dividing 18 feet by 3 gives us 6 by 6 divisions. That is, we have to divide the 18 by 18 feet panel into 6 in X and Y directions. Now assigning the loads to the slab panels. Live load as 40 psf, which was already specified. The superimposed dead load as 20 psf. Checking the loads specified. Now we have to assign the diaphragms to the slab so that the lateral force is distributed according to the stiffness of the members. Now replicate it to another story. Let us story 1 and select the diaphragms option as well. So the diaphragm is replicated as well. Now click on apply. So you see the diaphragm is replicated as well. Now the column support are to be made as fixed. It's all on you whether you want to design the column's base as fixed or pin. If the column is resting on pile caps, then these supports are to be taken as pin, as pile caps or piles does not take moments or are not designed for taking moments. For now we are considering it's on isolated footing which takes moment. Also the raft takes moment. Now we have to go to design overrides and select a special moment resisting frame, which is already selected. Now go to the concrete frame design preferences and select the ACI code 31814 for the design, and then incorporate the design combinations by adding the default design combinations. For the concrete frame, also check whether it has not considered the drift load cases into the combinations, which is important that drift load cases should not have to be incorporated in the combinations because that is just a serviceability check. The design combinations are there for the design of concrete. Now we have to specify the P delta options. Usually we use the same combinations or factor scale which we have specified in the load combinations. We would have taken live load if it was a high rise structure, but since it's not, so we are leaving the live load as it is and not incorporating in P delta options. Now running the analysis. After the analysis is run, we have to perform the important checks until the cross sections are finalized and then check the reinforcement of the column. whether it is within the limits of 1% to 8% for columns. Now click on concrete design frame. The design part is skipped right now. It is completed. We have to go to display design and check for rebar percentage to have an idea whether the steel is exceeding the limit or not. Let's go to column design and PMM envelope. The reason which I specified exterior interior individually was this one, that we can select exterior and interior individually here so that we can view the reinforcement individually. You can also specify it in descending order. And now checking for interior, the steel is 1% at max. Now the next part would have to be to make all the columns, whatever we got the cross sections, as a predefined one, not the auto select one. Auto select was to get an idea of the cross section which ETABS will take, incorporating the moments and other loads. Now assign them as the section which ETABS selected for them. Now for the interior columns, now design the frame again. Let's increase the font size for better visibility. See 14 by 14 exterior. Okay. So now run the analysis and then the design. Still not cross section size are finalized. We have to check for strong column weak beam for SMRF requirements and the drifts and torsion irregularity. But for now we won't be checking torsion irregularity since it is not a high rise or irregular structure. To understand how torsion irregularity is applied, you have to go to the video whose link is given in description. We have to check whether the column is slender or short. But since we are using software, so it is not important. If the column is slender, then the moment is magnified, but since we are using software, then it will automatically compute the magnifier factor if required. But the important thing here is that we have to check for the effective length factor, that is K. Conservatively for design, we take the effective length factor K as 1 if the column is supported at top and bottom. So go to summary. The K factor is 1. SOA and non-SOA factor is 1. That means the column is not magnified, so it's not slender. Randomly checking other columns K factor. SOA and non-SOA factor are still 1 and the K factor is 1. The effective length is equal to the total column's height. That means the total column K is taken as 1. The bar percentage is 1. So now we are done with checking the effective length factor K. The next thing we will be doing is checking the stability. Let's check for column rebar percentage first. So the rebar percentage is within the limit of maximum 8%, which is totally okay. So the size of the column is adequate up till now for the checks which we have applied. So all column steel is minimum at minimum, that is 1%. We have to further perform the stability checks, which I am continuously saying. Stability checks will include strong column weak being checked for the special moment resisting frame requirements. And usually the column's cross section size are revised in that check. So what is a strong column weak being check? It is the sum of nominal fracture capacity of column at a joint, and that must be greater than 1.2 times of the sum of nominal flexure capacity of the beam at a joint. So let's check here as 6/5 column beam capacity ratios. Let's turn off the beam's visibility, also the horizon, so that it's easy to view. Now if you have a close look, you can see some of the columns. The symbol is written as O/S, that means the columns are overstressed and do not pass the strong column weak beam check. That means the nominal fracture capacity of the beams multiplied by 1.2 times is greater than the flexure capacity of the column at that joint, and the combination used is UD 10. That is basically due to earthquake, which you can always check the combination in the define options. So now we have to increase the columns cross sectional sizes. Let's select the next higher size as 18 by 18 inches. Previously it was 14 by 14 inches. Now let's make it 18 by 18 inches. So interior column shall be named differently, but we can see the percentages in the show tables option. So we have increased the column sizes, and let's check whether the columns are passing the strong column weak beam check or not. There is no need to perform the other checks such as drift and other checks again if we have increased the column sizes. So I think the columns are okay in the sizes right now. This row is okay, this row as well, this row of columns as well, and the rest of the columns are okay with this size. Let's check the rebar percentage. Since design is an iterative process, so we have to apply different checks on different cross sections. If we increase the sizes too much, then the design would be uneconomical. We always have to consider three things when designing the structure: safety, serviceability, and functionality. But most of the things are usually considered over economic. So the seismic drift check, we have to calculate the story drift and shall not exceed 2.5% for the structures having 0.7 second time period and the structure having time period greater than 0.7 seconds. The limit is 2%. It is specified by UBC 97. So now we will be performing the drift check. First of all, we need to check the time period of the structure at mode 1. The time period of the structure at mode 1 is found ought to be 0.492 seconds. So the fundamental period is specified in seconds. Since the time period is less than 0.7 seconds, then the drift limit for our structure is 2.5% or 0.025. Now we will be checking whether the structure drift is within the limit or not. So now we go to the analysis, results, displacements, and then the story drifts. Click on OK. First of all, select the load combinations for the drift only, which be specified by amplifying the scale factor. Hold Control button and then select the rest 3. Specify the drift by descending order. So the maximum drift we are getting is 0.012, something like that. If the structure was failing in drift check, then we have to increase the lateral stiffness of the structure. That is, we can increase the moment of inertia of the column or shear walls if present, usually increasing the size of the columns. So the columns steel we are getting is 1%. So now we have to incorporate this steel in the main bars. The columns cross-sectional sizes are finalized, which are 18 inch by 18 inches. So quickly we will be revising the names. Or the dimensions of the columns in the drawing. It is just for demonstration purposes and it is a not to scale drawing. %1% steel means 0.01 times the gross section of the column, gives us 3.24 inches square, and the number 5 bars has area of 0.31. So dividing the area of steel required divided by the 1 bar area gives us approximately 10.8 something bars. But since we cannot provide bars less than 12 according to the situation we are given, we have to be symmetric in both directions since it is a square column. We could have been less than 12 bars, but if we don't have to compromise on the symmetry of the columns or the reinforcement symmetry. Now for special moment resisting frames ties. The limitations of the ACI code are presented as: the spacing S of the ties at the column ends shall be provided greater than the following 4 cases. At a distance L0, 6 times diameter of the smallest longitudinal bar, quarter of the smallest cross-sectional dimension, S0 4 plus under bracket 14 minus HS divided by 3. The value of S0 shall not exceed 6 inches and need not to be taken less than 4 inches or 6 inches. L0 shall not be taken as column span divided by 6, the depth of the member at joint face or the section where flexure yielding is likely to occur, where plastering hinges form. Or number 3 is 18 inches. The spacing of the ties shall not be greater than 2 times S outside the extent of L0. So L0 is the distance that occur at the joints. ACI limitations for special moment resisting frame ties. We have to check for confinement the total cross-sectional area of rectangular hoop ASH shall not be less than the confinement required by the column. The confinement is usually calculated as considering an important thing. Alternate ties criteria. If the spacing between adjacent longitudinal bars is greater than 6 inches, then we provide adjacent or alternate ties. Calculating spacing limitations for our conditions is shown. The first condition gives 6 inch, second 4.5. Similarly, we have selected the least. We have to select the least. Now further we have to check what ETABS is giving for the design. For that, first we will be doing the exercise for the exterior columns. Hiding the interior columns for time being. So the numbers are randomly increasing or decreasing. So in order to get the highest number for conservative design, since we are designing columns as typical, so we have to pick the highest number from the exterior columns, which we will get from the tables. Concrete column shear envelope. Now select the exterior columns and sort descending. The maximum shear steel we are getting is shown at the top, that is 0.2641. I think 2 legs of bars would not work with this area, so we will be needing to provide 4 legs. So the spacing of ties is equal to number of ties legs multiplied by the area of tie bar divided by area of steel. That gives us number 4 at 3 inch center to center. So quickly modeling 4 leg bars. So the legs are 4 in number on both the directions, so that I have detailed it in drawing so that you can understand in a better manner. So now we have provided 4 legs of shear ties in both the directions. Number 4 at 3 inches center to center rings or ties. So we have to copy this. To all of the columns. Since exterior columns are getting that much shear, so the interior columns will also be getting a high value of shear. So we are modeling that in all of the columns. Right now we haven't checked it for interior columns. So for exterior columns, for ground floor column and first floor column, we have incorporated the shear ties. Now checking for the interior columns. As expected, we are getting a higher value of shear steel at the interior columns in terms of inch square per foot. And the combination is UD content, that is again an earthquake combination. This roughly we will be requiring 4 legs of ties for this amount of shear steel required. Usually we don't provide the shear steel closer than 2 inches or 3 inches, because too close bars can not get a proper cover of concrete. So usually we'll apply limitation of the spacing between ties as 2 inches or 3 inches, that the bars shall not be closer than 2 or 3 inches. So now calculating for number 5 ties. The area of 1 tie bar into the number of ties legs divided by AV from ETABS. So we get number 5 at 4-inch center to center ties. So it is a high diameter of bar for shear. But since we are getting it, so we have to incorporate it, considering it is within the limits of the SMRF ties, which we have already checked. Now labeling the general nodes, the FC prime was 4 ksi and the F5, that is the yield strength of steel, is 60 ksi. You can add further nodes for the contractor if you wish to. Subscribe to the channel and visit the channel for much more ETABS tutorials and other softwares to come soon.